Welcome to Lecture 3 of Week 8. What we are covering in this lecture are some pretty obvious theorem statements. They are obvious because we have already spent quite a few lectures working with sequences and have developed a robust understanding of how sequences work. It turns out many of the properties of limits of sequences also carry over to limits of functions. We already mentioned this in the case of limits at plus and minus infinity. We will officially mention this in this lecture for limits of a function at finite points. Given that the statements are obvious, the emphasis of this lecture is not so much on knowing that the theorem statements are true, but rather I would like the emphasis on showcasing the similarities of a sequence convergence proof versus a function limit convergence proof. Specifically, how the epsilon n arguments we use for the sequence convergence theorems can be easily transformed into the epsilon delta argument we need for function limit theorems. In other words, I'm hoping that all the sequence convergence practice you have done up to now will allow you more flexibility when dealing with limits of functions. Let us begin. The first theorem is a theorem concerning arithmetic of limits. The statements read almost exactly the same as the case for sequences. We are given two functions such that the limit of f at a is L sub f and the limit of g at a is L sub g. Then we can conclude that functions formed by adding and multiplying f against g both have limits at a, and their limits are Lf plus Lg and Lf times Lg, respectively. For division, we need to also impose the condition that g does not vanish and the limit L sub g is not 0. This is just so that the function f over g makes sense as a function on the same domain, and that Lf over Lg also makes sense. With this, we can say that the function f over g also has a limit at a, and the limit is Lf over Lg. We will not spend too much time discussing this theorem. As I said, the results are sort of obvious and the proofs are the same as the cases of the sequences. I will, however, remark that the theorem also holds if everywhere you replace the two-sided limits with either one of the one-sided limits, either from above or from below. And the theorem still works if you make the same replacement throughout. Next, we'll talk about the comparison theorem. It is possible that the statement was not explicitly stated for sequences in this course, hence I will include a proof here to show the principle. For ease of reading, I divided the theorem on this slide and separately stated the assumptions and the conclusion. The hypothesis of this theorem requires that f and g are functions such that their limits at a both exist. Notice that I stated the theorem this time using the limits from above. I will also produce a proof using limits from above, but the theorem holds if you globally replace limits from above by either limits from below or by the two-sided limits. The third hypothesis required there to be some b bigger than a such that on the open interval from a to b, the function f of x is bigger than the function g of x. This third hypothesis gives the comparison. We only require this comparison to hold in a limiting sense. We do not require f of x to be everywhere bigger than g of x. Since the limit property only concerns what happens to the functions near a specified point, we only require the comparison to hold in an interval near the specified point a. Notice that since we're looking at the one-sided limit from above, it is only important that f of x is greater than g of x on an interval that sits above a. For the limit from below, we will need to replace this by an interval that sits below a. The conclusion of our theorem says then the limit of f is bigger than the limit of g. Let's give the proof. For convenience, let's write Lf for the limit of f and Lg for the limit of g. Our desired conclusion is that LF is greater than or equal to LG. For this proof, we will approach by contradiction. Suppose, then, that LF is strictly less than LG. Then, we can choose epsilon to be equal to LG minus LF over 2. By the contradictory assumption, we have that epsilon is positive. I choose an epsilon because I want to use the hypothesis that the limits of f and g exist. Remember, if your goal is to prove that the limit exists, I have to account for arbitrary epsilons and show that there is a corresponding delta in every case. But here, we already suppose that the limit exists. We just don't know how big they are. So we can make use of the existence of the limit by taking an epsilon of our choice and making the hypothesized convergence do its thing. Using that the limits of f and g converges, we had that for the given epsilon that I picked, there must be a corresponding delta f and delta g, such that on the interval from a to a plus delta f, the difference between f and LF is less than epsilon. And similarly, on the interval from a to a plus delta g, the difference between g and LG is less than epsilon. And so, taking the smaller of the two deltas on this smaller interval, we have that the value of the function f is at most LF plus epsilon, and the value of the function g is at least LG minus epsilon. And since LF plus epsilon is the same as LG minus epsilon, by our choice of epsilon, this means that f is less than g on an entire interval. However, we hypothesize that f is at least g on an entire interval from a to b. It therefore cannot be the case that it is also less than g on an interval from a to a plus the smaller delta. So we derived a contradiction. As an aside, we use proof by contradiction rather than contrapositive this time because we made use of some of the hypotheses in deriving the contradiction. A contrapositive proof will proceed by showing that the negation of the conclusion implies the negation of the entire set of the hypotheses. Our proof here shows that some of the hypotheses, together with the negation of the conclusion, implies the negation of one of the remaining hypotheses. The next theorem we will present is the analog of the squeeze theorem, but for function limits. Our hypotheses here are for three functions f, g, and h. We assume that the limits of f and g agree, and we assume that the three functions are ordered with f bigger than h bigger than g on some interval. Notice that we are assuming a limit from above for this theorem, and we speak of the ordering holding true on an interval ab that sits above a. We can again rewrite the theorem in terms of limits from below, which will require making the interval for which the ordering holds true be below a. Our conclusion for this theorem is that the limit of h also exists and equals L. Notice that this squeeze theorem is not immediately a consequence of the comparison theorem from before. The difference is that in the comparison theorem, we assume that the limits of f and g both existed and obtained a relationship comparing their values. In this theorem, we did not assume that the limit of h exists. Had we assumed that the limit of h exists, then indeed, by the comparison theorem from the previous slides, we must have that the limit of h is greater than the limit of g and lesser than the limit of f. The limits of f and g agreeing, this means the limits of h must be L also. But since we did not assume that the limit of h exists, the previous theorem does not apply, and our main goal is to prove that h in fact converges as we approach a from above. Here is the proof. It is in spirit very similar to the squeeze theorem for sequences. Again, our goal is to utilize the convergence of f and g to say something intelligent about h. So we start by asserting that the convergence of f and g tells us that for every epsilon positive, there exists delta f and delta g, such that f is within distance epsilon of L on the interval a to a plus delta f, and g is within distance epsilon of L on the interval a to a plus delta g. We also know from our hypothesis that on an interval AB, G is less than H is less than F. Combining the three inequalities together, we have that on the common interval of the three, this would be from A to the smallest of A plus delta F, A plus delta G, and B, we have firstly f is less than L plus epsilon, secondly g is greater than L minus epsilon, and thirdly h is between g and f. Chaining all of those together, we find that h must be between L minus epsilon and L plus epsilon. Since epsilon is arbitrary, we have found an interval sitting just above a on which h is within distance epsilon of L and showed that h converges to L. That's it for this lecture. Next time, we will finally introduce the definition of continuity.